So I think we'll try and start now. It seems like most people have managed to get seats, which is great. So it's really wonderful to see so many people here tonight. I'm just going to introduce myself because tonight I'm both the host and the speaker. And this is a little bit by design because we had no idea what tonight was going to be like. So I wanted to give the first talk, not because I'm an egotist, that's incidental, but just because I wanted to, make sure it went smoothly. There should be a few seats. There's a few seats down here in the bottom left and on some of the sides, which you might be able to squeeze into. Sussex Universe. So Sussex Universe is a thing that has existed for more than a decade. It was originally a set of lectures organised by students in the School of Mathematical and Physical Sciences. In fact, some of the early organisers, who are now moved on to other things, teachers, etc., are actually in the audience today. I won't point at them. Maybe I will later. Oh no, I've lost them. There we go. We've got one over there, Kat. These lectures began really as an opportunity for researchers, faculty in the department, to tell their students and then members of the public about some of the amazing research that we do here in Sussex. So this continued on until early 2020, and then something happened. Obviously, I don't need to go into the details of what happened, but that changed a lot of things. Obviously, events like this were suddenly cancelled. What we did then was a group of us, bored out of our minds at home, decided to try and move these lectures online and actually then try and reach a bigger audience, not just through the power of the internet, but also by diversifying the talks that we did. And so at that point, Sussex Universe changed again, and we had a whole load of YouTube talks, so we were doing talks streaming on the internet. That never really, made us completely happy, but we liked this idea that we actually broadened the talks beyond just the department. We liked the way of actually reaching wider audiences. And so one of the things that we've learned from the pandemic is that we will record things, and in the future we may even stream these events as well. So Will, my PhD student and one of the original runners of Sussex Universe, right in the very middle, is recording me right now doing this. So this will appear on our YouTube channel at some point. Fast forward a few years and things have slowly been getting back to normal, and we're now in a position that we feel like we can do these events again. But it is really great to see so many people here. But like I said, these events are now fundamentally different from the events that we were doing 4 years ago because we've diversified them, right? We've diversified beyond maths and physics. Okay, we've diversified to, in this first step, all of the science schools at the university. If you want more information, then please do look at our website. This is something that's very much in progress. If you've got any queries, you want to ask us a question, you want to make a speaker recommendation, if you want to give a talk yourself, particularly if you're faculty or a student here at Sussex, then please just do email us as well. And before I start speaking myself, I just wanted to advertise some of the talks that we've got coming up. So as I said before, this is no longer constrained to just maths and physics. Okay, we're going to be covering all of the science schools here at Sussex. And so our next talk, which is going to take place in 2 weeks' time, is from Mark, over here, who's an engineer. I won't read out the title because I haven't got my glasses on and I've forgotten them all. So I'll try and guess them from the pictures. We have a talk about bees, okay, with an excellent pun. And then we have, I think, one of the ones that I'm really looking forward to from Gillian here about kindness. So something completely different from what we saw before, but should be a really exciting talk. And then we've got Simon Peters, who is, again, somebody else from my department, so he's a physicist, who's also going to be talking to us. Now, Simon's talk is going to be a little bit different because his is what's called a professorial lecture. And that's where, when people are made full professor at the university, they're kind of expected to give one of these talks, these commencement talks. So it'll be a little bit more celebratory than the normal talks. And so this semester is very much a trial run. So we've got 5 talks over this semester. We're really using this to kind of gauge the interest, gauge the demographic, and just see if there really is an appetite. I'm hoping today isn't just a fluke, and that people will come back, every 2 weeks and come and see this excellent range of talks that we've got. So on that note, I'll stop babbling, and I'll talk about what we're here to do today, and that's to talk about first light with the James Webb Space Telescope, or JWST. So I already introduced myself once, but I'm Dr. Stephen Wilkins. I'm the head of astronomy here at Sussex. I'm also a reader in astronomy, and I'm also a public engagement fellow, which means that I'm paid for some of my time to actually go and do things like build exhibits and give lectures and go into schools. Okay, so I always like to start any talk that I do with actually, giving a little bit of a broader introduction to myself and my career path, particularly for those of you who are students or maybe thinking about becoming a student. This is what my path was. Okay, so as you can maybe tell by my slight northern twang, I was born in Leeds in West Yorkshire. I then decided to be an undergraduate at the University of Durham doing physics and astronomy. I then moved south to go to the University of Cambridge, where I did my PhD in astronomy. I then moved west and was a researcher at the University of Oxford. And now almost 10 years ago, which really is an astounding amount of time because so much has changed in that time, but it really feels like yesterday, I moved here to Sussex and I became a lecturer in physics and astronomy, and then I was promoted to senior lecturer and most recently reader. And today, as I mentioned before, I'm currently head of astronomy, and I'm also director of outreach and public engagement, which is why I'm here as your host tonight. Okay. And what I'm going to do today is I'm going to talk about a really special project, so the James Webb Space Telescope, or the Webb Telescope, or JWST, depending how you like saying it. Okay, so a little bit of an introduction to the telescope. I'm then going to tell you some of the mechanics of the telescope, and then I'm going to get to the bit that I think everybody's most interested in, and seeing some of these beautiful images that have been leaking to the media over the last couple of months. And it really is the last couple of months. This is, incredibly cutting-edge science that we're doing here. So this is what Webb looks like, or this is a visualization of Webb. And so Webb here, or JWST, is really our flagship astronomical observatory today. It's the scientific successor to two other observatories, one called Hubble, which has a 32-year history and hopefully many people are aware of, but a small telescope called Spitzer as well. And after many, many years of delays and in fact decades of development, this project finally launched on Christmas Day in 2021. Okay. Now, if you had paid attention to the media and you'd seen some information about this, you might be mistaken to think that this is a NASA project. That's not true. It's a combination of NASA, the European Space Agency, which includes us, and the Canadian Space Agency. But more than that, there is contributions from hundreds of universities across the world, thousands of researchers, scientists, technicians, engineers. Probably tens of thousands have contributed to this project just so far, let alone who are going to use it. Okay, so this is an incredible international contribution, and anybody who's paid any tax in this country will have contributed to this project. So it is yours as much as it is anybody else's. So as I mentioned, Webb is the scientific successor to these two other telescopes, Hubble and Spitzer here. Okay, so this is Hubble, this is Spitzer. What you're now seeing is all of these telescopes to scale. Okay, so straight away you can maybe guess why Webb is so transformative compared to these two, in that it's just much larger. Okay, so if we compare in this visualization the actual size of the mirrors of the telescopes, you see that Webb is around 5 or 6 times larger than Hubble and is around 50 times larger than Spitzer. And so when you make a telescope much bigger, you're able not only to collect more light and see fainter objects, but also see them in much more detail. That's not the only reason why Webb is different from these predecessor projects as well. Okay, so Webb also has a whole range of other capabilities. Really, really importantly is it has the ability to do spectroscopy. Now what spectroscopy is really summed up in this really simple image over here. So what you have here is that light is passed through a prism in this case, and we're splitting the light up into its constituent wavelengths. Now by doing that, we can actually learn about the processes, the physics behind what produced that light in the first place. And when I talk about some of the science that Webb has done, I'll go into the depths and details of some of those there. Now the spectroscopic capabilities, Hubble and Spitzer had some very limited capabilities, but not very much. Webb, however, is really built around this and really using this to answer some really key science questions. But probably the most important aspect of Webb, differentiating itself from other observatories, including those on the ground, is the light that it can detect and see. So Webb isn't a telescope that will see the same light as our eyes. It's designed to look at the infrared. So infrared light is light which is longer wavelength or lower energy than the visible light we can see with our own eyes. And this little diagram over here, you can see that Hubble was originally designed just to look at the visible light, but actually over time its capabilities expanded and now can view the UV all the way into a little bit of the infrared. Spitzer was always designed to kind of cover the infrared as well, but then Webb is coming in over here and really rapidly transforming what we can learn about the infrared. So why do we care about the infrared? Why is the infrared interesting to us? Why have we built our next big telescope to be an infrared telescope? Okay, so what is the infrared? I've already mentioned what it is from a simple scientific point of view, but let's look what else it can do. Well, just to give a little bit of history first of all, infrared light was actually discovered by William Herschel, a very famous astronomer from the United Kingdom and from Germany, and it was actually discovered, like many early scientific discoveries, entirely by accident in 1800. So the way that Herschel actually discovered infrared light was by doing a very simple experiment that we repeat to this day. What he did was basically have something like this. He had sunlight passing through a prism, and what Herschel did was he placed a thermometer over here in the visible spectrum. And Herschel noticed that the temperature of that thermometer was higher than the ambient temperature in the room. So what Herschel interpreted then was that actually that sunlight is heating that thermometer up. That's not really a big surprise. If you go out on a sunny day and kind of don't look directly at the sun but point your face at the sun, you can feel the sun's heat on your face, right? That's your face absorbing this extra radiation from the sun. But what Herschel did was also place a thermometer over here beyond the red end of the spectrum, so beyond where he could see light with his own eyes. And he noticed the same thing. He noticed that that thermometer recorded an increase in temperature compared to the ambient temperature in the room. And so Herschel's great ersatz then, which made this not just an accident, was that there is extra light that he couldn't see with his own eyes that's been absorbed by that thermometer. And so this is the infrared. Okay? And we now know, right, by building different detectors, that in fact the electromagnetic spectrum stretches both ways away from the infrared. Okay, so we go into the UV and the X-rays, and then on the other side we go from the infrared and into the radio waves as well. And so this really began, our ability to probe the universe in the infrared. But the infrared is really tricky, and that's because our atmosphere actually absorbs most of the infrared. So this is the actual second most technical diagram I'm going to show tonight, so don't be put off, there is only one more after this. And what I'm showing here is the fraction of light which is absorbed by the atmosphere as a function of the wavelength of the light. So over here in the X-rays, our atmosphere actually absorbs all of that light. Now that's really good because X-rays are very damaging for us. Okay? Same is true of the UV as well. Our atmosphere is actually protecting us from this energetic light which can cause things like skin cancers. As we go into the visible though, we see that the atmosphere suddenly becomes transparent, and this allows us to see things like the sun lights up the world. But then as we move into the infrared over here, things become complicated, and our atmosphere starts to absorb the light from the sun and other objects. But then, it gets better again as we move into the radio, the atmosphere becomes very transparent. And this is what enables a huge amount of our technology today, right? So I'm sure everyone has a phone in their pocket, I'm using Wi-Fi right now. That's enabled because our atmosphere is transparent at these wavelengths. But the consequence of it being not transparent at infrared means that if we really want to learn about our universe in the infrared, we need to get above as much of the atmosphere as possible. This is possible, actually by building balloons or by flying planes, but that doesn't actually give you very good images. And so our primary way of observing the universe in the infrared is to go into space. Okay, but what is the infrared showing us? Okay. What I have here is a really boring picture. You probably didn't expect to see a picture of a steel rod tonight. But what we have here is a collection of steel rods. One of these steel rods has been heated up to a very high temperature. And when you heat a material up to a very high temperature, it starts emitting light. Actually, that's not quite true. It's always emitting light. It just turns out if you heat it up to a high enough temperature, it emits visible light. But the point here is actually this cooler bit of the steel rod, and in fact these are the steel rods, they're still emitting light, they're just emitting infrared light that we can't see with our own eyes. And so what we can do with infrared astronomy, one of the things we can do with it is actually observe things which are cooler than stars, cooler than things that will produce visible light. So one of the places where we routinely use this technology on the Earth is images like this. This is actually a picture of my daughter now from about 4 years ago. But what you're seeing here is a picture of my daughter as viewed by an infrared camera. And what you're seeing here is actually my daughter, like all of you in the room, are actually glowing in infrared light. If I turned out all of the lights in this room and I pointed an infrared camera at you, you would all be glowing still. So this technology has a huge number of uses here on the Earth, but actually the place that most people interact with it is via crime procedurals, where you might see, the bad guy running away from the police get out their infrared camera because it's dark, and they can easily spot the warm person from the cooler surroundings. Okay, so I'm not claiming here that we're going to use infrared astronomy to look at people on other planets, or am I? I'll get back to that in a bit, but it has a huge number of uses. Okay, so in fact there's a whole range of astrophysical phenomena, things like asteroids, some types of stars, planets, galaxies, that all produce infrared light. There are some that only produce infrared light, so there are some astrophysical phenomena that we couldn't see at all without infrared light. Okay, so this really fills in some gaps. Moreover, the more information that you have, so combining visible light and infrared light and other wavelengths of light, that allows you to understand things in more detail. And in fact, we're now at a point where this is really our main limitation, that we want to collect together all these different wavelengths to try and understand everything in the universe. Okay, so I'm now going to tell you a little bit about the spacecraft, James Webb the spacecraft. Okay, this is what it looks like. And for a long time, I would make jokes that this doesn't look like a telescope anymore. It looks like some kind of, 1980s alien spacecraft in a really rubbish game. Right, would always look something like this, very blocky. Oops. Okay, but if we look in detail, it really does have the same characteristics of things like Hubble, just in a slightly different configuration. So first of all, we can see the primary mirror. This is the thing that collects the light and then begins to focus it. There is a secondary mirror over here, so the light comes in, bounces off onto this one, and then bounces back through the middle of the primary mirror. Once it does that, it goes to the instrumentation suite. What I mean by this is really just the cameras and the spectrographs, the things that are going to take the images, record the data. Okay, but things that Webb has that Hubble didn't have are, for example, this sun shield over here. Right, and I'll tell you more about that in a second and why we have it. It's also got to communicate with us down here on the Earth, so it has a communication system and also a power supply via these solar panels. Probably the most striking feature of the spacecraft, other than its shape, is its mirrors. So its mirror is actually made up of 18 individual mirrors, so these individual hexagons over here, and these are all gold colour because gold looks really cool. In fact, it's gold because gold reflects infrared light much better than things like steel or aluminium. Okay, steel and aluminium are really good for making mirrors in visible light because they reflect virtually all of the visible light that falls on them. But that's not true when you move into the infrared. And it turns out the best reflector of infrared light, at least the one that can be polished, is gold. And so the entire telescope has about 50 grams worth of gold. That's actually not very much money when you consider the overall cost of the project. Okay, so please don't melt it down for gold. Okay. This is now showing the configuration of all 18 mirrors. This is now an image, this is one of my favorite images for a long time. This was taken now about 4 years ago, just when it went in to do some testing. What I really like about this image is that immediately after this image was taken, they put the telescope in there, they jiggled it around in a vacuum, and then they brought it out again. And then they found some screws on the floor. Maybe explaining why the telescope was delayed for, an extra 6 months to a year. There's lots of really funny stories, but I've actually stopped talking about them now that it works. Okay. Instrumentation. So, a telescope is only as good as its mirror, it's only as good as its location, and its instrumentation, its cameras. If you have a rubbish camera on your telescope, it's just not going to work very well. Okay, and so in fact, lots of the development of Webb has been into its instrumentation, and it has 4 different science instruments. I won't go through the names of them, but by having 4, this actually gives Webb not just expanded capabilities, but also redundancy. Okay. Really important though is that one of these cameras, arguably the most advanced of these cameras, was built and designed here in the UK. So this is the Mid-Infrared Imager, or MIRI, that was led by my colleague Gillian Wright up in the ATC at Edinburgh, and was tested in various bits of the UK before being shipped for integration. And so this is why the UK has really heavily contributed to this project, as much as any other European country, and only really dwarfed by the US. But then again, the US is 6 times bigger than us in terms of population. Okay. Now, because Webb is an infrared telescope, this means you have to modify the design compared to visible telescopes. And the reason for that is that, things that are relatively warm, like room temperature, are producing infrared light. When you're using your infrared telescope, you don't just want to take a picture of the telescope. right? So you want to keep the telescope as cool as possible to minimize the amount of infrared light coming from it. And the way that Webb does this is in two primary ways. So it has a sun shield, and it has a different orbit from Hubble. Sun shield first. This is what Webb looks like with its sun shield entirely unfolded. This material here is the world's most advanced crisp packet. That wasn't actually a joke, because this material is basically crisp packet. It's basically a very thin layer of plastic, aluminized. Okay, so we've got actually several layers of this crisp packet material. In fact, I felt some of this material, not the actual stuff that was used, but you can feel it, and it feels like a crisp packet. It actually feels like a more flimsy crisp packet, which is, you know, disconcerting, but also kind of cool as well. And the point of this sun shield over here is to reflect as much of the other light that's out there that we don't want to look at away from the telescope as possible. But this only really works if the bottom of the spacecraft is always pointing at the hot things in the sky. And that's where Webb's orbit comes in. So Webb doesn't orbit the Earth. Okay? If it did, it would be, you know, complicated, because you've always got the Earth nearby, you've got the moon in a different part of the sky, and the sun in a different part of the sky. What Webb does is actually orbit the sun, but it orbits the sun at a very special point in the solar system called the Earth-Sun Lagrange point, or the second Earth-Sun Lagrange point. Now this orbit takes exactly a year to go around the sun, but it's actually a little bit further away from the sun than the Earth is. And for those of you who are studying physics, the way that this works is that, you know, the Earth is providing a little bit of an extra tug on that orbit, because otherwise you'd expect it to take longer. But what this means is that the telescope can always point its bottom, essentially, at all of the bright things in the sky. So the Earth, the moon, and the sun. So that allows the telescope to get very, very cold without having to resort to things like having a supply of liquid helium, which can also be used to keep things very cool, but runs out. Okay. Now, the negative consequence of this is that this is actually quite far away. So this point is around 4 to 5 times the Earth-Moon distance, so around 1.5 million kilometers away, which, you know, poses problems if you wanted to repair it. You can't. Also poses problems in terms of actually getting the data down from the telescope, in that you need very big, you know, radio telescopes here on the Earth to actually get that data back, and they're always in demand. Okay. So after many, many years of development, so really Webb was a twinkle in astronomers' eyes for a decade before we even started doing anything, and then it took roughly 20 years to actually make. Right, this is technology which had never been made or designed before. This is entirely novel, and this is just showing how advanced it is that it took that long. But after all this time, it was actually launched on Christmas Day from the European spaceport, which very confusingly is in South America. I must admit, this was a really, really bittersweet moment for me, because I've been involved in Webb for, you know, virtually all of my academic career. I've done a lot of the public engagement for Webb across the country and across the world. And so I was invited to this big party we were going to have when it was due to launch in October. I was told there was going to be free-flowing champagne, there was going to be dignitaries there, I was going to be, you know, congratulated for my efforts. But then, you know, it launched on Christmas Day, and so they said, oh, we're not going to do it because, you know, it's Christmas Day. And so in the end, I ended up watching the launch of Webb from an iPad in my parents-in-law's house in Leeds, a place called Gipton, if anybody knows it. Yeah, Gipton. Little bit of inner city Leeds. I was watching it on an iPad while I was peeling carrots, making Sunday dinner. So it wasn't quite what I was hoping, but at the same point, I can say something poetic and say, you know, best Christmas present ever. Blah, blah, blah. I would have much preferred the free-flowing champagne. Okay. So you can see Webb launching over here. And actually, you can tell this is Webb. Oops. You can tell this is Webb because if you look really carefully there is the little Webb logo. I always really hate this image because the UK's flag is on the other side of this booster, and so you never actually get to see it. So nobody believes that we're involved in it. There it is again. Okay. So on to the science. And, you know, when I gave this talk 4 months ago, this was before we had had any of the results. So I was talking about what we are going to do with the telescope. And now I'm going to tell you about what we are already doing with the telescope, and what we've already done, as well as looking forward to the future. But the point I want to make before I do that is that the combination of Webb's larger mirror, its optimization, the new technology means it's 10 to 100 times better by virtually any metric than its predecessors. And when you start changing the way we look at our universe by that amount, right, you start, revolutionizing science. We're going to discover stuff that we haven't anticipated. But also key with Webb is actually its flexibility. It's not designed to just do one thing other than look out, right? It's going to be used, or it already is being used, to explore everything from our own solar system all the way to the most distant objects in the universe. And so what I'm going to do now is just take you through, a really small slice of the highlights of what we've already discovered and what we might discover. Okay, I'm going to start nearby and take our way out. So, planetary systems and the origins of life. This rather grandiose statement was not my choice of words. This is words that NASA and ESA have put in my mouth. But hey ho. This is not a Webb picture. This is Jupiter. Hopefully people know this. And although we can study Jupiter in really great detail by sending a probe to Jupiter and therefore getting really close, what we can't do so easily is observe Jupiter all the time, and we can't observe it, necessarily in the infrared unless we've sent an infrared telescope out there as well. But that's very, very expensive to do. And so we've actually been able to observe Jupiter in the infrared. In fact, we were able to do this from the ground before, and when you do this, you see something completely different from what you see in the visible. And in fact, you see this delineation between these bands of storms much more clearly. But this image is no longer interesting to me because we now have this image. And this was Webb's very first image of Jupiter. This is actually quite a crude image because we're going to observe Jupiter, many, many more times over Webb's mission. But just in this one image alone, there is a huge amount of interesting science. So first of all, again, you see the delineation between these different bands. And this is telling you that these different bands have different compositions and different temperatures. And so by comparing these images with the visible images, we learn more about how Jupiter's atmosphere works. Okay. You see the great red spot is really brightly visible now. We also see some other interesting features over here as well. We see this great black spot. Don't be worried if you've ever watched the sequel to 2001: A Space Odyssey, 2010: A Space Odyssey. It's not monoliths, right? It's actually just the shadow of a moon, and there's another one over here. If we look really closely, you can see this band. This is actually Jupiter's ring system. So Saturn isn't the only planet to have a ring system. Jupiter has this very, very faint ring over here. And you can see this little moon as well. Actually, the team that took this is actually based up in Leicester. So again, more UK involvement over here. And I actually asked them what they thought was the most interesting. Why did they want to take this image? And it turns out it's nothing that I've pointed out. It turns out the thing that they're really interested in is the fact that at the top of the planet and at the bottom of the planet, it's glowing more than the rest of it. Actually, it turns out what you're seeing there is the northern and southern lights, the aurora borealis, aurora australis, but on Jupiter. And so they're really interested to study what those areas look like. I won't say they don't care about the rest of it, but the reason why they did it was to look at these bits. And this is just, kind of showing that there is so much depth just in this one image. But what we're going to be able to do with Jupiter is observe it many, many more times, right, and get much more detail, but also see it rotating over time, right, and try and understand what causes these storm systems. More recently, this was a couple of weeks ago, Webb observed Neptune. So we have Neptune over here. So obviously because Neptune's a little bit further away, it doesn't fill as much of the image. But again, you see Neptune's ring systems really prominently in the infrared now, whereas you don't really see them anywhere near as prominently in the visible. You also see a handful of Neptune's moons over here. And you can see even on the surface of Neptune, you see some areas are much brighter than others. But actually what's most interesting for me about this image is that Triton over here, this is one of Neptune's moons, turns out to be much brighter than Neptune at these wavelengths. And that's because what Neptune is made of actually absorbs lots of infrared light. So Neptune actually looks relatively dark in the infrared, right? It's just that we've got a very big telescope over here. Whereas Triton, its moon, just reflects a lot of infrared light, so it looks very bright. Okay, it's smaller because it's smaller, but it turns out it's actually brighter once you count all of the energy coming from it. Hold that in your mind for a second, the fact that some materials absorb more infrared light than others. Okay. Moving beyond our own solar system, I think one of the most exciting things that Webb will do is actually observe planets around other stars. Now, for the last 25 years or so, we've been able to discover planets around other stars. here's an example of one planetary system that we've actually taken images of. This was from the ground, and you can see this was back, 10 years or so. And what you're seeing here is a nearby star, which would be in the middle over here. We've subtracted the light from that star, and when you do that, you can see there are 4 objects that are moving around that star, right? So this is over many years, lots of images put together. And so it turns out that each one of these objects here is actually a planet. So what you're seeing here is a solar system not that much unlike our own. Those planets actually in this case are all a bit boring to me though, because they're like the mass of Jupiter and they're cold. The point here is though, is that with Webb, we're going to be able to do this experiment, but much closer to the star and on much smaller planets. So Webb will at some point in its mission be able to do this same experiment, but with planets like the Earth. And that actually even opens up the idea of, if you get really clever about your techniques, you can maybe even say that these planets have, continents on them and oceans. But it doesn't stop there. Because actually just observing a planet like this is not even the best way of finding and studying planets around other stars. Okay. The best way is to take advantage of something called the transit technique. So if you have a planetary system which is aligned just right with the Earth, every now and then a planet will pass between us and its parent star. And when that happens, you have a mini eclipse. Okay, so when that happens, the light from the star dips ever so slightly, okay, often by a fraction of a percent, and then goes up again. And it will do this every time it goes round. And so you get a really, really clear signal that there is a planet going around that star. And so this is how, this isn't actually how the first planet was discovered. This is how we've discovered most of the planets out there in the universe. Today we've discovered, it changes every week, but we discovered of the order of 6,000 or 7,000 planets, mostly using this technique. And that's really cool because actually we're discovering planets which are the same mass and maybe even the same kind of surface temperature as the Earth. And I think that alone is, amazing. But what's even cooler is, when these planets do this, if these planets have an atmosphere, and the atmosphere over here is denoted by this semi-transparent band, it's very exaggerated, but if they have an atmosphere, some of the light from that star has got to pass through the planet's atmosphere. And as it does that, depending what's in the atmosphere, that atmosphere will absorb some of the light, and it will imprint the composition of that atmosphere on the light that we can record. And so the idea there is that we can actually then learn about what that atmosphere contains. Okay, to see this in another way, what I'm showing you here, this is sunlight, right? So this is sunlight now kind of split up into its constituent wavelengths, and then we've made a nice visualization by stacking it all together. But if you look very carefully at this image, you see that it's not just continuous, you see there are all these dark lines. And these dark lines actually correspond to different elements or ions in the sun's atmosphere absorbing light at that particular wavelength. And so this is a technique that astronomers have been using for, almost 200 years now to actually study what is in the atmospheres of things like stars, but now planets. Okay? It turns out that helium, the second most abundant element in the universe, was actually discovered in this way using an image like this, so looking at the sun. So helium was first discovered not here on the Earth, but actually in the sun's atmosphere. I always forget which line it is, but I think this one over here is helium. And so by seeing that and not being able to match it to anything we've seen on the Earth, allowed us to infer the existence of this element. Okay, second most abundant element in the universe after hydrogen. But we can use the same idea to study the atmospheres of now planets around other stars. And in fact, when we're looking at planets around other stars, the reason why the infrared becomes really useful is that we look at molecules. And we look at molecules like water, like methane, like carbon dioxide, and like ozone. So ozone is just oxygen, but with 3 oxygen atoms. And so we're now at a position that we can start trying to detect these molecules in the atmospheres of planets around other stars. Now, as you can imagine, if we discovered things like oxygen and carbon dioxide and water in the atmosphere of a planet, particularly a temperate planet, that's a good indication that maybe it's habitable, or maybe that's even inhabited already, in that, oxygen is really tricky because most of the oxygen on the Earth is produced by life. Now, you can get oxygen via, geological processes, but seemingly not the right amounts. And so the idea is that actually a detection of an oxygen, although not a smoking gun of plant life, is a really good indication that there might be plant life on that planet, right? And this is within grasp now that we have Webb. Webb hasn't done this yet, but what it has done, and what it did in its first week of operation, was discover water in the atmosphere of a planet. So this is the final technical diagram I'm going to show you. And what you have here is, again, a spectrum. So the amount of light as a function of the wavelength of light. And in the spectrum of this planet, okay, you see all these wiggles, right? And these wiggles are characteristic of water in this planet's atmosphere, right? So we're part of the way there. And so this will only change as we collect more data and we observe more planets and we keep moving forwards. Right. I should say right now, actually, the images that I'm going to show you are the sum total of about a week worth of Webb, right? We're going to have Webb for potentially 20 years, right? This is barely scratching the surface of what we can do. So moving out a little bit, one of the other areas that Webb will really transform is our understanding of the formation of stars and planets. And the reason for this is that stars and planets form in regions like this. So this here is a region of our own galaxy called the Eagle Nebulae. This is, again, not a Webb image. This is an image taken actually by an amateur astronomer, and I've missed out the credit over here. Hopefully they're not in the audience. That would be a massive coincidence if they were. If you are, please don't sue me. But the point here is actually this is a place where stars and planets form. But the problem is that when stars and planets form, they form in these massive clouds of gas and dust. And those massive clouds of gas and dust absorb visible light. If we zoom into this region in the middle, you might be more familiar with what I'm showing here. This is now a Hubble picture, and this was my favorite image of all time until recently. This is an area called the Pillars of Creation. And in these, huge pillars of gas and dust, we have new stars, new planets, maybe new aliens being formed every day. The problem is, we can't see that happening because all we can see is the dust. But it turns out the more you move into the infrared, the more you're actually able to look through the dust. And so Hubble did this experiment. By moving as far into the infrared as it could, it was able to look through all of this dusty material, which is all over the place, and now see, thousands more stars, right? So going from this, maybe there was 200 stars in this image, now to having thousands of stars. And you're able to start looking through this dusty gaseous material. You can see over here, you can maybe even see all the way through it. But over here, it's still problematic because where the stars are forming are still enveloped in this material. So with Hubble, we weren't able to quite get there to the sites of star formation. This is another image that Hubble took, and this is a region of our own galaxy again called the Carina Nebula. Again, this is a star-forming region. The reason why I show you this one now is that this was one of Webb's first observations as well. And so this is Hubble's image, this is Webb's image. The detail here is now astounding, but actually there is no way this projector can do this justice, because this projector has maybe 1,000 pixels across it. The actual image that I'm showing you here from Webb has something like 20,000 pixels. So the actual image is much better. So what I'm going to do is I'm going to take this little bit over here, this little bit that's sticking out because it looks funny, and I'm going to zoom in on that. This was the view from Hubble, so that's kind of cool. You can see all this weird structure, you can see some stars, but when you look at this same area of Webb now, you see again tens, hundreds of times as many stars, much more detail. And in fact, this is just one quick image with Webb, and one quick image at certain wavelengths which are not even designed to do this experiment. With another part of Webb, in fact using the mirror camera that was mostly developed here in the UK, we can do this experiment and actually look at the sites of star formation in this object, and therefore learn how stars and planets formed. This is another really recent example. This is an area of a nearby galaxy called the Tarantula Nebula, which has actually just formed a whole collection of stars. So when stars form, they form from all this gaseous material. And what you're seeing here is, actually millions of individual stars that have recently been born in this region. And they've kind of used up or excavated all of this gas in the middle. And so we're just seeing the leftover gas now. And so if you compare this with Hubble, this is just, astounding as well. Going further out, so I'm moving further and further away now. This is again a Hubble image of a relatively nearby grand design spiral galaxy. Some of the most beautiful objects in the cosmos, because the idea that very simple physics gives rise to these beautiful spiral patterns. But when you look at the same object with Webb, you see something very different. So in this image, which is in the visible, you see all these dark areas over here. Now, when people first looked at these objects, they thought that was an absence of stars. But we now know that's actually quite the opposite. This is where stars are forming, because it's the dusty material which absorbs the visible light. And if we look in Webb, in the right wavelength, we get almost the opposite image now. What you're seeing in this image is actually the dust itself glowing from the light of those new stars. And so this is why I said, actually, only by combining images in the infrared and visible together can we really understand what's going on here. Okay. Going about further, we have here a quite famous collection of relatively nearby galaxies. They're called Stefan's Quintet. I'm going to anglicize that as Stephen's Quintet, obviously because it's my name, because I'm an egoist. But this is a collection of galaxies which are quite special because they're actually all, well, 4 of them are merging together. Okay, so they're crashing into each other. Each one of these objects over here is a collection of billions of individual stars and lots of gas and dust. And what's interesting is when they crash into each other, they trigger a whole new burst of star formation. And if you look at this same object now with Webb, you start seeing that actually all of these galaxies are already connected. There is material which is glowing that are linking them all together. Okay. And you can see that this one over here has this big tail of material, and this is a telltale sign that it's already kind of started interacting with its neighbors. Okay. So what I've just showed you is, I think, amazing science that we haven't been able to do before, but it's not actually the science that I do here and not the science that my team work on. What we work on is the distant universe. Okay. So when we look out in the universe, we're not seeing it as it appears today, we're seeing it as it appears at some point in the past. So when I look at you, I'm seeing you as you actually were a fraction of a second ago. When I look at the moon, I see it as it appeared about a second and a half ago. If I look at the Carina Nebulae, it's about 8,500 years ago. So that's now, encompassing virtually all of human civilization, human recorded history has happened in that time. If I look at this galaxy, one of my favorites, Centaurus A, we're seeing that as it appeared 30 million years ago. So this now, expands well beyond humanity's closest ancestors, right? So we're now pushing even further back, right? Humanity was nowhere near around at this time. And we can take this further. Stefan's Quintet, we're seeing it as it appeared several hundred million years ago. And we can actually push this back to 1.5 billion years ago. And, with Hubble and now with Webb, pushing all the way back close to the beginning of the universe's history. So this little blob here was one of the very first galaxies that I discovered back 10 years ago when Hubble was refurbished for its final time. We were tremendously excited about this little red sausage, right? Because this is a galaxy more distant than any galaxy that we'd seen before, right? And even though it looks like a little red sausage, it was tremendously important to us at the time. And so with images like this, so stepping out a bit, this is the Hubble Ultra Deep Field, our deepest image of the universe until recently. This image over here contains about 10,000 individual objects, most of which are galaxies, and those galaxies stretch back almost over the entire history of our universe. There are billions upon billions of stars in this image that contribute to all of these. But this is really like a snapshot of the entire history of the universe, or almost the entire history of the universe. I say almost because Hubble doesn't quite get there. Hubble is actually a relatively small telescope. So the size of Hubble's mirror is only about this high, so about 2.5 meters. Okay, so Webb is 5 times larger. And this means it can see fainter things and it can see them in more detail. Especially when you combine that increase in size with, increase in sensitivity of its cameras. And so here is a patch of sky as observed by Hubble. This is actually a very deep image taken by Hubble. And this is a special patch of sky called SMACS 0723. Doesn't have a very good name. It will become more important soon. And this is actually a galaxy cluster. So this is a special bit of sky where there are more galaxies than other bits of sky. And you can kind of see that. There are all these kind of elliptical galaxies laying around over here. And this is what we saw with Hubble, right? In a shorter period of time, this is what we see with Webb. So you go from seeing, a few hundred objects to now seeing close to 10,000 individual objects. But again, this screen cannot do this justice. So I'm going to focus on this thing over here, my favorite galaxy in this image. This is what it looked like to Hubble. This is what it looks like with Webb, right? So over here, we knew there was something weird going on there, right? But here you can count almost on your fingers how many objects there are. Oops, too far back. Now we can see there are, probably, of the order of high hundreds of objects in here that we could detect. All of these little things over here. Many of these are individual galaxies. And we see this very unusual galaxy over here that we christened Biden's Slug. The reason why we did that is that this was the very first image that was released by NASA and ESA. And it turns out President Biden decided to release it ahead of schedule. And they had this really... This has been recorded, so I'm not going to say anything else about that press conference. You can ask me my details later. But they released this image, and so this was the very first one released, and this is the one that's closest to my science, obviously. And we saw this, this slug thing over here. Actually, the more that I look at it now, it looks like a disembodied tongue to me. That's even more gross. It turns out this galaxy over here is actually a very special type of galaxy. Well, it's not a special type of galaxy. Something special is going on. And the special thing that's going on is that this is not what the galaxy should look like. This galaxy probably looks like just a nice normal spiral galaxy. But the light from that galaxy has passed by this really big galaxy on the way, and it's distorted that light. And it's left it with this weird telltale shape over here. And this is a phenomenon called gravitational lensing. This is really useful to astronomers because although it distorts what images look like, it actually boosts their flux. It boosts the light we can get from them. So these clusters of galaxies actually act like, huge natural lenses in space. But this was also, a prediction of Albert Einstein's general theory of relativity. And this is just a really beautiful example of it. This one is perhaps not that interesting because it's still a relatively nearby galaxy. This little thing over here with the almost beads, this is super cool because this is a galaxy which is much further away. Right, and you're actually seeing some of its detail there. This is a really, really super cool thing. And if we flip back over here, you can see there are a whole load more of these things, these arcs. These are all galaxies that have been magnified and distorted. So what else can Webb do that Hubble couldn't? Well, as I mentioned, Hubble only observed some tiny bit of the infrared. That's important because as we look further out into the universe, the light from more distant galaxies gets shifted into the infrared. And that's because of a phenomenon called cosmological redshift, which is all to do with the expansion of the universe. Basically, the further away something is, the more its light is pushed into the infrared. Okay? So myself, my team, and my collaborators, we were jumping on this early data and data that our programs got, and we started trying to discover these galaxies that we couldn't see before. And so this is an example of one. This little red blob over here, this is just the first of what we expect to be many. But this is just making the point here that JWST has now observed galaxies which are present only a couple of 100 million years after the Big Bang. These galaxies are more than 30 billion light years away. These are just ridiculous numbers, right? Only rivaled by, Elon Musk's net worth. We actually got into, this is an example of why I hate Twitter. My collaborator Steve, another Steve, over in UT Austin in the US, he's the lead of the survey that we were looking for. And it turns out we discovered this interesting galaxy on his daughter's birthday. So instead of celebrating his daughter's birthday, he was busy in the office doing work, which, he had to think of something to compensate for this. So he said, let's call it Maisie's galaxy, Maisie being his daughter. And we all kind of said, yeah, let's do that. That's kind of fun. And, the press will love that, right, because they'll jump on it. And the press did. This got us more press attention than we might otherwise have got. But then Twitter happened. And apparently, naming a galaxy after your daughter as a joke, is against the UN's Outer Space Treaty, because apparently it's tantamount to claiming a bit of space for a nation state, which is against the Outer Space Treaty. So at that point, I regretted typing Twitter in. I just wanted to see what was happening, and I just regretted seeing the Twitter storm, mostly from professional astronomers complaining that we shouldn't do this because it's against... Funny story though. Webb isn't just going to find galaxies like this. It's not just going to find new red blobs like Hubble was. It's not just going to give us galaxies that we can look at. It's going to dissect their light in more detail. So using the same techniques that I showed you before about exoplanets, we can learn about the composition of these galaxies, these really distant galaxies. We can work out what they contain. The reason why this is really interesting is because when the universe was born at the Big Bang, however you want to describe it, the universe just contained hydrogen and helium. And all of the other elements, all of the other elements that are vital for our existence, for the Earth's existence, were all created subsequently. And most of them were created when stars died, which is quite sad. But when stars die, they leave these beautiful images over here. So these are planetary nebulae and supernova explosions. And what you're really seeing here is the enriched leftover remains of stars. Now those remains of stars end up forming new generations of stars and planets like the Earth, right? So the only reason why we have a rocky planet like the Earth with things like oxygen, carbon, iron on them is because stars lived and died in the past. And so what we want to do with Webb is look at these galaxies and work out, well, actually how many of those elements did they have back then? And can we trace how these elements are built up over time? Okay. And so the final Webb image that I'm going to show you in a second, this is an example of one of these objects. This is not particularly distant, this is in our own galaxy, but it serves a purpose. This is the Southern Ring Nebula observed by Hubble. Okay, so this is a star which is actually on its way to dying. So the star is here, and it's losing some of its outer layers. This is what Webb sees. You now see so much more detail. You see these individual, almost concentric shells of material being given off. When I look at this, I think it looks like an iris, so a person's iris. You can see this kind of mottled pattern, and it's just, astounding. The final bit of science is into the unknown. So whenever you build something, revolutionary like Webb is, the interesting things that you're going to learn is not the questions that you already know about, it's actually the things that you haven't yet anticipated. But as a segue, whenever I hear this phrase, into the unknown, what do you think I get? Anybody want to volunteer what they associate into the unknown with?
Frozen.
Frozen! So, as a parent of 2 small children, whenever I hear this phrase, which is used by NASA, right, all I can see and all I can do is, in my head, sing the song. I'm not going to do that for you because I can't sing.
What if we try?
You'd have to pay me a lot of money to make me sing that. You also probably didn't expect to see Donald Rumsfeld in this talk either. But Donald Rumsfeld had this quote. I know it's quite long, right, and it was, the context here was actually justifying invading a country. But he said something that's actually quite important, that there are actually things out there that he phrased as unknown unknowns, things that we hadn't yet anticipated, that we, just can't anticipate. And actually the idea is that probably the most exciting part of Webb's mission is not anything that I've shown you at all. It's actually the new stuff that we haven't anticipated that it might discover. And in fact, astronomy in particular is littered with this kind of stuff. Every time we look at the universe in a new way, we discover something new and weird and puzzling. Right? So things like black holes, dark matter and dark energy, they have these names because we're confused by them. Right? I'm actually, I'm quite agnostic. But when I think about the history of astronomy, every time we look more carefully at the universe, I do get this little sense that, maybe the universe is built just to annoy astronomers or to give us something to do. Because every time we think we've solved something, right, we look a little bit closer and no, we haven't. So gravity is a really good example. Newton was like, I've sorted gravity for you guys, right? And then Mercury didn't behave like it should do, and there's other little problems. So Einstein came in and said, all right, I've fixed gravity for you. Turns out that doesn't even work. So general relativity, doesn't play well with other theories of physics. And so general relativity is also not the end of the line either, right? And so every time we look a little bit closer, the picture gets more complicated. These are not just details, right? Actually, dark matter and dark energy together make up 95% of our universe. They're not just minor details that we don't understand. They're big swathes of the universe that we have no idea, maybe not no idea, but close to no idea what they are and how they work. So for me, the most exciting things is not the things that I've shown you, is not even the things that I work on, but the things that we might discover that we haven't yet anticipated. And so I'll end there and just say that, this is the end of my talk, but it's really only the beginning. We're only really a few months into Webb's mission. The images that I've shown you are less than a week of Webb collecting data. We're already playing around with so much more data than we can barely deal with at the moment. And my team will soon, with our collaborators across the world, get even more data at Christmas. And so it's a really, really exciting time. And so I'll end there and hopefully have time to answer some questions. And while I do that, I will leave this advert on. So thank you for listening. What time we're on? Oh, we're 7 o'clock, so maybe we have time for a few questions. Question right there. You're very fast.
This could, some chat on YouTube. It could be noise, but they seem very excited about the idea that Webb disturbed the Big Bang Theory. Is this noise or?
So the question there was, has Webb disturbed the Big Bang Theory? So this, if it's the one that I'm thinking of, this is something close to my research. So a group of scientists said, we've discovered these really unusual galaxies, right? Really, really unusual. And in fact, they hadn't realized this, but they're so unusual that if they're real, they fundamentally break, how we think the universe operates. So there's something called the concordance model of cosmology, called lambda CDM, basically what we think about cosmology. And they claim to have broken it. What I would say is it's incredibly premature. We don't understand the telescope yet. It almost certainly, isn't correct yet. But Webb has the power to do that. I'm being quite conservative in that sense. I don't think it is. I think in fact, I have an alternative explanation. I think it's much more mundane than what they've claimed. But there's been a few cases of this as well. I'm going to go for the question right there because it's closest to me.
On a related question, if the Big Bang occurred 13.7 billion years ago or thereabouts, how can we see 30 billion years away?
You caught that really nicely. So yeah, we think the universe is about 13.8 billion years. So you might think the most distant objects that we could see is 13.8 billion light years away because light can only travel at the speed of light. But it turns out in that intervening almost 14 billion years, our universe has expanded. And so the measurement of 30 billion years is what you would measure if you had a really, really long ruler today. Not that that's practical or at all possible, but it's one measure of how far that is away. And I often planted that just so I can answer that question. Just so I have an easy question that I can do. Yep?
Yeah, I was going to say, with regard to the more recent times that we're going to be living in, can we use this to analyse certain molecules of closer planets in order that certain molecules can only exist at a certain temperature?
Yes, so we can certainly point Webb to anything nearby where we can understand in more detail. The only bit of the universe that Webb can't see is everything closer to the sun than it. So we can't point Webb at the sun, Earth, Moon, Mercury, Venus. Everything else is fair game. And so, for example, we will eventually point Webb at things like comets, where you have these huge eruptions of complex molecules, including things like alcohol in them. And we can use Webb and its infrared spectroscopy to actually learn about some of these molecules. I don't know the details of all of that bit of science, it's not my area, but it's certainly a possibility. Webb can see, ultimately anything that's not, enclosed by the Earth's orbit. And so we will point it everywhere, because we're going to have it for 20 years. You were fastest up there.
I remember a few months ago seeing that the telescope was hit by a large rock or something, a large comet. How did we deal with the damage, and what's the plan for future damage?
So large means something different to astronomers, to everybody else. And in this context, actually large means really, really small. It is true that Webb early on in its mission was hit by something. Now that something was, teeny tiny, like smaller than a millimeter. We always knew that was going to happen because space is full of stuff. It just so happens that Webb got hit earlier by something relatively big, earlier than we hoped. When that happened, it has almost certainly affected the telescope, so made it, harder to see faint things. But the effect so far has been quite small. Now, if we got hit by something that size many, many more times, then the telescope gets worse and worse and worse. And in fact, it is true that the telescope will just get worse from now on in. It will be hit by stuff in space, including cosmic rays, which are really fast-moving particles. They will degrade it, things will break. So Webb at the moment is the best it will ever be, except that the way telescopes work is that you collect data over time and then you can add it all together. So it's never going to give us as sharp images as it does today, but by stacking images together, you can see much further. So it is a concern. As far as I'm aware, we haven't been hit by anything again like that. So I think we're fairly confident about, the predictions. We've got telescopes in the same place. We've had other probes there, so we know how much stuff there is there. So we think we just got unlucky quite early on. If you got really unlucky though, each of the individual segments of the mirrors can be adjusted independently. So if one of them, it would never get cracked, but if it got seriously damaged, you can potentially defocus that entire segment and avoid that light. It's difficult, but it can be done in some way. I think there was a question in the middle there.
So, as you showed on your slide, you said for spectroscopy you need the whole visible light spectrum. But then Webb has access to infrared light. So, does it also have access to visible light for spectroscopy, or?
It doesn't. So Webb is designed solely to work in infrared light. And the reason why it doesn't work in visible light is because gold doesn't reflect visible light particularly well. So the reason why gold looks gold is because it actually absorbs all of the blue light. So it reflects only the red light, which is why it has a reddish kind of orangish tint. So you could in principle have made electronics that allow it to do that, but it would have been a waste. Because we've still got Hubble, and we might actually have Hubble for a bit longer if anybody saw the news recently. And we're also building, big telescopes on the ground where, the visible light, we can go through the atmosphere. So one of the next major projects that's going to be built on the ground is something called the Extremely Large Telescope. Great name, because actually, as an aside, you shouldn't name things after people. It's always a bad idea. I can answer that question if you want. But we're building this, huge telescope called the Extremely Large Telescope, which is an optical telescope, which will basically match what Webb will do, but in the visible. But it has to be a lot bigger because it's still got to deal with the atmosphere. Is there a follow-up question as well?
Follow-up question. So, can you still do spectroscopy accurately in infrared as well?
Yes, you can do spectroscopy in the infrared. It's harder than in the visible because the longer the wavelength of your photons, the more difficult it is. But you can still do it as well as we need to do it to answer the science questions. So, Webb was built with certain science questions in mind, which included things like, water and ozone on exoplanets, right? You can always build a bigger telescope to get finer resolution. Question there?
Yeah. Is there any chance that it's going to be able to find the elusive ninth planet?
So the question there was about an elusive ninth planet, not Pluto, which was demoted because it deserved to be, but for the last couple of years, astronomers have been claiming that actually maybe there is still 9 planets. There's just a planet which is, much further away, but also relatively massive. And the way that we've tried to detect that, or the way we think it's being there, is that it has a gravitational influence on the other planets. The problem is that that planet is so far away from the sun that it's probably quite dark, right? So it doesn't reflect very much light. But it might be cool enough that it produces enough infrared light so it could potentially be found by Webb. The problem is, though, that Webb has a really tiny field of view. So at any one time, Webb only sees actually about 2 millimeters square on the sky, right? So to map the entire sky, 2 millimeters at arm's length on the sky, makes more sense. So to actually map the entire sky with Webb is, just not going to happen. But there are a couple of new space telescopes coming up in the future. There is the Euclid Observatory, which is a pure European one, and then there's the Roman Observatory, which will map large areas of the sky, which are probably going to be better for finding that potential planet than Webb will. What we could do with Webb, though, is if we had an idea where it was, we could look in that region and see. But we have no idea. I'm not even convinced it's there because it's a very subtle effect, and it could be caused by something else, even something more interesting. I think there was a question over there first.
How long does it take to process?
So I think the question there was how long does it take to process the images? So we get the images from Webb actually very quickly, within a day or two of them being taken. And then how long it takes to process them is a really complicated question. You can process them, very quickly if you've got a big computer. But it turns out what we've found over the last few months is that there's lots of manual intervention you need to do as well. So at the moment, it's not quite as simple as you press go. That's what we want it to be able to do. We want to press go and get the really nice science-ready images out. At the moment, there's lots of kind of tweaking we need to do because we don't understand the telescope and the cameras yet. But soon, in a year's time when we do understand, I think you'll be able to take an image one night and actually be able to do science with it in a couple of days. So very, very rapidly. And in fact, I'm going to use that to point out one of my favorite things is that actually most of the Webb data is immediately public for anybody in the world. Not just astronomers, you can go and download the actual raw data. So if you're an amateur astronomer or you like playing with Photoshop, you can actually go ahead and download that data and make your own versions of these beautiful images. And in fact, Reddit and Twitter is full of people who are not astronomers, not by the professional astronomer label, but they're making actually much nicer images than I could ever do because they've got complementary skills in Photoshop and software like that. But if you want to learn how to use that software, go download some web images and make them yourself and make them pretty, because then they become yours as well. If you download a raw image, you create a color image from that raw images, that's yours, right? And you get to keep that. There's a question down here, and then probably one or two more after that, and then I need a drink.
How maneuverable actually is Webb? Because if you said it has to block the sun from one angle, right? You can't actually see things past the sun.
That's a great question. So the question there was how maneuverable was Webb being? And the limitation for Webb is that it always needs to keep its kind of bum pointing towards the sun. So if we imagine that this is Webb and the sun is over here, what Webb can do at any one time is only kind of go around in a circle like this, right? And it can kind of tilt a little bit this way. So at any one time, if you try and visualize this in 3D, all Webb can really do is see like a ring on the sky. Okay, so at any one time, it has actually a quite restricted view of the entire sky. But every 6 months, it goes around the sun. So every 6 months, every 6 months it does half of the way around the sun. And because it can do 360 like this, every 6 months you'll be able to see anywhere on the sky. But most of the sky, it can't continuously monitor, which is a shame. There are bits of the sky, the bits that are up there and down there, where it can always look, right? So it can always kind of point up and down if the sun's in the middle, but the other bits of the sky it can't. And that is, again, one of the major limitations of Webb that you've picked out. Thanks for that. And there was a couple of questions there. The first one with the hand up right at the back.
I was just going to say, what determines the longevity of telescope Webb's nature? And I'm assuming it's not a definite point, but at what point, let's say, would we decommission its data for unreliable use?
So initially, what was going to limit the lifetime of the telescope was the fuel. So it needs fuel to maintain its orbit and move around. But it turns out the launch engineers did such a good job in actually plotting the orbit, along the way, that they actually conserved much more fuel than they were expecting. So the amount of fuel will last 20 to 30 years. But what's probably going to limit its lifetime is, this question before, it's going to get hit by stuff. Something will break because things break, even in space. So it's likely there'll be something like that which affects it over time. But, I think we're quite optimistic that we're going to get, I would say, between 15 and 25 years out of Webb. Whereas at the beginning, we were kind of saying maybe 5 to 10. Other than that, it doesn't have any extra fuel. It's just really something breaking. And that's very difficult to anticipate. But, we've done lots of tests with the electronics. And it's got a lot of redundancy as well. So it's got these 4 cameras. If one breaks tomorrow, you can still do most of the science with the other 3. Unless it's Miri, If MIRI breaks, then that's a real shame because MIRI has unique capabilities. I think there was a question just behind you. Yep, right at the back.
With regard to the gravitational lensing, is it possible for any technique to be used to rebuild an image of a star or galaxy?
Yep, we do that. So there is a thing called image reconstruction where you take, oh sorry, the question for people who didn't hear is, with gravitational lensing, you distort galaxies, you change their shapes. The question was whether we can actually make them look like they originally looked, and you can. It requires actually knowing exactly where all the mass is that's doing the gravitational lensing, which is tricky because the light doesn't always follow the mass. So things like dark matter, you can't see it, but you can get an idea and you can reconstruct them to some extent. I think just one more question. Oh no, I'm not going to answer your question. You can ask a question another time, Via.
That's not too bad.
No, you can ask me the question another time, but somebody else might. There's a question over there, really, really adamant. I'm going to go for that one.
Thank you. Yeah, I'm wondering, you talk about the view of the sky as being 2 millimeters at arm's length. What's the resolution within those 2 millimeters?
So within those 2 millimeters, you have about 20,000. No, sorry, about 8,000 pixels. Right. So you can work out the total number of pixels that you could cover the sky with if you observed the entire sky with Webb. I haven't done that number, but it's one with lots of zeros after it. Be a cool one to do. But there's no way that Webb would ever be able to, cover the entire area of sky like that. I'm going to stop answering questions now. I'm going to hang around outside again if people want to answer me some questions, but I could do with, at least some water, and I know people need to get away as well. But thank you for coming. Please don't make this your only visit to Sussex Universe. We have these 4 other great talks coming on, and if we can keep this level of audience, that would be fantastic. Thank you.